So I was showing you the notes for the theory of projectile motion in the case of oblique projection. I would like to continue the same. I will continue my previous class discussion. The maximum height reached in the previous class, I have shown you this formula. H equal to maximum height reached by the projectile above the horizontal plane of projection is given by u sin theta whole square by 2g. Up to here I have shown you in the earlier class up to question number 12. I would like to continue the discussion. I would like to show you the notes for continuation. The maximum height reached in terms of time of flight of the projectile is given by capital H equal to gt square by 8. Next I would like to show you the calculation for horizontal range of the projectile. The horizontal range of the projectile can be written as equal to the horizontal component of velocity to time of flight. Or we can write R equal to Vx into T. Here R represents the horizontal range, Vx represents the horizontal component velocity, and capital T the time of flight. The horizontal component of velocity projectile remains same at all the instants during the motion under gravity. So you can write Vx equal to u cos theta, and time of flight is given by, as I discussed in the earlier class, 2u sin theta by g. If you want to copy the notes, you can take a pause and copy the notes. Those results which you need to remember or which we may directly use in numerical problems, I am numbering them. Numbered 13, 14 you can see. In some of the questions we use the principle equation number 14 directly. We may not write the formula in letters in some questions. So those who are writing the notes, you can take a pause and copy the notes. So this you can write 2 sin theta cos theta. You can write sin 2 theta from elementary trigonometry. So you can write horizontal range R equal to u square sin 2 theta by g. So for a given initial speed of projection, the horizontal range is proportional to the value of sin 2 theta. So horizontal range of the projectile will be maximum when sin 2 theta is maximum. Maximum value of sin 2 theta equal to 1. So for a given initial speed of projection, horizontal range will be maximum when sin 2 theta equal to 1. That is when 2 theta equal to 90 degrees or theta equal to 45 degrees. So for a body projected from level ground, the horizontal range of the projectile when it returns to the level ground, or the horizontal range of the projectile when it returns to the horizontal plane to the point of projection, will be maximum when the body is projected at an angle of 45 degrees above the horizontal. To find the maximum value of R, you have to take theta equal to 45 degrees in the equation number 15, or sin theta equal to 1. So those who want to copy the notes, you can take a pause and copy the notes. For a given initial speed u, maximum horizontal range is equal to u square by g. That is equation number 16. Next I am going to show you the working for the equation of trajectory of the projectile. The horizontal displacement of projectile in the case of oblique projection given by x equal to u cos theta into t from the equation 2 I have written earlier. From same equation you can write t equal to x by u cos theta. So if you want to copy the notes, you can take a pause and copy the notes. Vertical displacement y is given by u sin theta into t minus half gt square. From the equation number 4 I have written earlier. You can substitute t equal to x by u cos theta in this equation to get the equation of the trajectory. That is, to get the equation of trajectory, you have to eliminate the time t from the equations for x and y. So substitute t equal to x by u cos theta. The first term on the right side u gets cancelled, sin theta by cos theta, you can write tan theta. So equation of the trajectory of the projectile is given by y equal to x tan theta minus gx square by 2u square cos square theta. This is equation number 17. This equation may also be used directly in some of the problems. So those who want to copy the notes, you can take a pause and copy the notes. This equation of trajectory can also be expressed in terms of horizontal range of the projectile. I am going to show the calculation for that. To show the equation of the trajectory, to write the equation of trajectory in terms of horizontal range, can write the formula for horizontal range R equal to u square sin theta by g. From same equation, you can write u square equal to gr by sine to theta. You can substitute this value of u square in this equation 17, which I have shown you just now. Y equal x tan theta minus gx square by 2u square cos theta. You can substitute u square equal to gr by sine to theta. So g gets cancelled here. Acceleration due to gravity g gets cancelled in the second term on the right side. So you can write sine to theta equal to 2 sine theta cos theta in the next step. So 2 gets cancelled there. Then sine theta by cos theta, you can write tan theta. So those who are writing the notes, they can take a pause and write the notes. So in continuation, you get y equal to x tan theta minus x square. I have denominator cos square theta. I have written as cos theta into cos theta. One cos theta you can cancel. Sin theta by cos theta you can write tan theta in the second term on the right side. So you get y equal to x tan theta minus x square tan theta by r. If you take x tan theta common outside, equation of trajectory in terms of horizontal range of the projectile is given by y equal to x tan theta minus x tan theta whole multiplied by 1 minus x by r. You can write the equation of trajectory in terms of horizontal range as y equal to x tan theta whole multiplied by 1 minus x by r. Those who are writing the notes, they can take a pause and write the notes. Next, I would like to discuss the relation between the maximum height reached and angle of projection and horizontal range r. We have maximum height reached in terms of the initial speed u and angle of projection is given by u square sin square theta by 2g. And horizontal range of the projectile is given by r equal to u square sin 2 theta by g. Can divide the h with r or multiply h with reciprocal of r. So h into 1 by r will be equal to, you can substitute h equal to u square sin square theta by 2g. And 1 by r means you can write g by u square sin 2 theta. You can cancel u square here. You can also cancel g. And the next step, you can write h by r equal to sin square theta by 2 sin 2 theta. Next step, you can substitute sin 2 theta equal to 2 sin theta cos theta in the denominator on the right side. Sin square theta, you can write sin theta into sin theta. So 1 sin theta you can cancel here. So you get h by r equal to 1 by 4 tan theta, or tan theta equal to 4h by r. This is equation number 19, which we may use directly in some of the problems. So those who are writing the notes, those who want to copy the notes, if they require more time, they can take a pause and copy the notes. Next, I am going to show you the two special cases in oblique projection. Case 1, I have already discussed the calculation behind these special cases, but I am going to show you the notes for the same. If two bodies are projected with same initial speed u at different angles to the horizontal, then their horizontal ranges will be equal. The sum of their angles of projection is 90 degrees or pi by 2 radian. If h1 comma h2, if capital h1 comma capital h2 are the maximum height reached for the two complementary angles of projection, then the range r in each case is given by r equal to 4 into root of h1 h2, or you can write r equal to half g capital T1 capital T2. So you want to come with the conclusion or write the notes, you can take a pause and write the notes now. I'm going to show the calculation behind this conclusion. Where T1 and T2 are the times of flight for the two complementary angles of projection. You can also write some of the maximum heights reached in the two cases u square by 2g. So I have shown you the conclusions of the case 1, where two bodies are projected with same initial speed u at complementary angles of projection. I am going to show you the working calculation part for these conclusions, because the calculation behind the conclusion may be required for board examinations, for the questions given in board examination. Horizontal ranges are equal if u square sin theta 1 by g equal to u square sin theta 2 by g equal to r. I do not range in each case by r. So sin theta 1 equal to sin theta 2. That means the two angles 2 theta 1 and theta 2 must differ by must be supplementary. So 2 theta 1 can write 180 degrees minus 2 theta 2 because sin 180 minus theta is equal to sin theta. There is a relation in trigonometry. So if sin 2 theta 1 is equal to sin 2 theta 2, we can write 2 theta 1 can be written as 180 degrees minus 2 theta 2. So if you divide the equation with 2, next step. So r 2 theta 1 plus theta 2 180 degrees, or theta 1 plus theta 2, we can get 90 degrees. That means if two bodies are projected with same initial speed u at different angles theta 1 and theta 2 to the horizontal, then their horizontal ranges will be equal if sum of their angles of projection is 90 degrees. Theta 2 can write 90 degrees minus theta 1. Product of the maximum heights is given by h1 into h2 equal to u square sin square theta 1 by 2g. h2 can be written as u square sin square theta 2 by 2g. So you can substitute theta 2 equal to 90 minus theta 1. The next step, you can take 1 by 2 into 1 by 2, 1 by 4, you can carry to left side. So 4 h1, h2 can write u power 4 into sin square theta 1 into sin square 90 minus theta 1 by g square. So those who are writing the notes, you can take a pause and copy the notes. Those who want to copy the working part, they can take a pause and copy the working part. Sin 90 minus theta 1, I can substitute it as cos theta 1. So 4 h1 h2 equal to u power 4 into sin square theta 1 into cos square theta 1. This you can write it as multiplying over the denominator with 2, putting a common square here. Here 2u square sin theta 1 into cos theta 1 by 2g whole square. 2 sin theta 1 into cos theta 1, you can write it as sin 2 theta 1. Denominator 1 by 2 whole square, you can write 1 by 4. U square sin theta 1 by g gives you the range r of the projectile. So you can take 1 by 4 to left side, 4 into 4 h1 h2, you get r square. Or r square equal to 16 h1 h2, or r equal to 4 into root of h1 h2. This is the calculation for the conclusion I have shown you directly in the beginning. So those who want to copy the calculation, they can copy this calculation. They need more time to copy the calculation, they can take a pause and copy the calculation. So already discussed earlier that maximum height reached by the projectile can be expressed in terms of time of flight as h equal to capital H equal to small g into capital T square by 8. So maximum height reached by the first projectile can be written as h1 equal gt1 square by 8 and h2 equal gt2 square by 8. So substitute these values of h1 and h2 in the previous equation. R equal to 4 into root of h1 into h2. You get r equal to 4 into root of gt1 square by 8 into gt2 square by 8. So you get 4 by 8 into gt1 t2, or you get r equal to half gt1 t2. So this is the calculation for second part, second conclusion in the case 1. So if you want to copy the working, you can take a pause and copy this working. In the same special case, that is when the two bodies are projected with same initial speed at complementary angles of projection, so the maximum height is given by h1 plus h2 equal to u square sin square theta 1 by 2g plus u square sin square theta 2 by 2g. You can take u square by 2g common there, and you can substitute theta 2 equal to 90 minus theta 1. Then the two bodies are projected at complementary angles of projection. You can substitute sin 90 minus theta 1 equal to cos theta 1 in the next step. So you get h1 plus h2 equal to square by 2g whole multiplied by sin square theta 1 plus cos square theta 1. Sin square theta 1 plus cos square theta 1 will be equal to 1 from elementary trigonometry. So you get h1 plus h2 equal to u square by 2g. That means if the two bodies are projected with the same initial speed u at the complementary angles of projection, then the sum of the maximum heights reached by them will be equal to u square by 2g. Next, I am going to show you the next another conclusion, special case 2. First, I am showing the conclusion. Later, I will show you the working for the conclusion. The two bodies are projected with different initial speeds at different angles to the horizontal, such that their times of flight are equal. And the maximum height reached by them will also be equal. So if you want to copy the conclusion, you can take a pause and copy the conclusion. Next, I will be showing you the working for this conclusion. The ratio of the maximum height reached by the two projectiles at a given place is given by h1 equal gt1 square by 8, h2 equal gt2 square by 8. That means I have used the relation between maximum height and time of flight. Maximum height reached in terms of time of flight is given by capital H equals small g to capital T square by 8. So maximum height reached by the first projectile can be written as h1 equal gt1 square by 8. Maximum height reached by second projectile is the same place can be written as small g into d2 gt2 square by 8. So h1 by h2 will be t1 by t2 whole square. Or h is proportional to square. So if t1 equal t2, then t1 by t2 will be 1, then h1 will be equal to h2. Converse is also true. If the maximum heights reached by the two projectiles are equal at a given place, then their times of flight will also be equal. Again, if t1 equal t2, and 2u1 sin theta 1 can be written as 2u2 sin theta 2 by g. Here u1 and u2 denote the initial speeds of projection of the two projectiles, and theta 1 and theta 2 denote the angles of projection of the two projectiles. That means if the times of flight of the two projectiles are equal, you can conclude that vertical component of initial velocity must be the same for the two projectiles. Then there is some conclusions which you have to remember. In the case of two conclusions I am going to discuss in oblique projection, I would like to show you the conclusions first. I will later show you the calculation behind these conclusions. The conclusion, first conclusion. So you have put the heading some conclusion to remember. I am not going to show you much conclusions, much number of only two conclusions I am going to show. The projectile is found at the same height, small h, at the instance of time t equal t1 and t equal t2, respectively after projection. And the time of flight of the projectile is given by capital T equal to t1 plus t2. And small h you can add half g t1 t2. Similar conclusion I have discussed even for in the case of vertical projection. If you want to copy the conclusion, you can take a pause and copy the conclusion. So when the projectile returns to the second conclusion, to the horizontal plane to the point of projection, its speed will be equal to u and its velocity makes angle theta below the horizontal. An angle theta below the horizontal. That means same angle theta with which it is projected upwards. I'd like to show you the calculation for these conclusions. Now I'd like to show you the calculation for the conclusions I have just shown you on the screen. So I would like to show you the calculation for the first conclusion. For this we use the equation for displacement y in the vertical direction given by uy into t plus half ay into t square. That means using the equation s equal to ut plus half at square for motion in the vertical direction. Uy is the initial velocity in the vertical direction, that you can write u sin theta. Ay is acceleration in the vertical direction is equal to minus g. The body is suppose found at the same height h. at the two instants of time t equal t1 and again at t equal t2 after projection. Then we can write y equal to h at t equal t1. And one more equation, similar equation, you can write y equal to h even at t equal to t2. So then you can write h equal to u sin theta t minus half gt1 square at the instant t equal to t1. For the instant t equal to t2, you can write h equal to u sin theta into t2 minus half gt2 square. At both the instants, the projectile is found to be at the same height. The body is projected with initial speed at angle theta above the horizontal. The body is found at the height h at the first time at the instant t equal to t1. The body is again found at the same height y equal to h at the instant t equal to t2. The trajectory of the projectile is a parabola. So for the instance t equal to t1, I have written this equation h equal to u sin theta and t1 with half gt1 square. For the later instant, we can write at t equal to t2, y equal to h, u sin theta and t2 minus half gt square. So left hand side is same in these two equations, so you can equate the right hand side. So you get u sin theta into t1 minus half gt1 square equal to u sin theta into t2 minus half gt2 square. So you can take the terms containing acceleration due to gravity on the left hand side, the terms containing u sin theta to the right side. So t2 square minus t1 square, you can write t2 minus t1 into t2 plus t1. So divided by t2 minus t1, can write it as 2u sin theta by g. So t2 minus t1 is a common factor. Both numerator denominator gets cancelled. So t1 plus t2 equal to u sin theta by g. As I discussed here, 2u sin theta by g gives you the time of flight of the projectile. Therefore, t1 plus t2 will be equal to the time of flight. So if the projectile is found at the same height, I mean same vertical height h at the instant of time t equal to t1 and t equal to t2 respectively after projection, and the time of flight of the projectile is given by capital T equal to t1 plus t2. And you can substitute the value of u sin theta from this equation. From the same equation you can write g into t1 plus t2 by 2 equal to u sin theta. You can substitute this value of u sin theta in this equation on the right side. So you can find h in terms of t1, t2. Substitute h u sin theta equal to g into t1 plus t2 by 2 into t1 minus half gt1 square. This can be simplified to get the conclusion I have given you. This you get gt1 square plus gt2 t1 minus gt1 square whole divided by 2, or you get h equal to half gt1 t2. That means if the projectile is found at the same vertical height h at the instance of time t equal t1 and t equal t2 respectively after projection, then we can write h equal half gt1 t2, and time of flight of the projectile is given by capital T equal t1 plus t2. This conclusion I have shown you on the screen already. In case you are interested to copy this working also, you can take a pause and copy this working. As I discussed earlier, the magnet belongs to the projectile, and the projectile is at a vertical height y above the horizontal plane of projection, is given by v equal root of u square minus 2gy. So when the projectile returns to the horizontal plane to the point of projection, that means when it cuts x-axis, we choose the horizontal direction through the point of projection as x direction. So when the projectile returns to the horizontal plane of projection, it cuts the y-axis, it cuts the x-axis, I'm sorry, not y-axis, it cuts the x-axis. Then we can write y equal to 0. When you substitute y equal to 0, you get v equal to root of u square minus 0, or v equal to u. That means magnet belongs to the projectile when it returns to the same horizontal plane through the point of projection will be equal to u. When the projectile returns to the same horizontal plane through the point of projection, the magnetic velocity will be equal to the initial speed of projection. If you use the equation v square minus square equal to as for motion in the vertical direction, you can write vy square is equal to ui square minus 2ay to y. So when the projectile ay, you can write minus g. When the projectile cuts the x-axis, y equal to 0. If you put y equal to 0, you get vy square minus uy square equal to 0, or vy square equal to ui square. Or we can write vy equal to plus or minus ui mathematically. But the vertical component of initial velocity at the point of projection is directed vertically upwards. But when the projectile returns to the horizontal plane of projection, the vertical component of velocity vy will be directed downwards. But horizontal component of velocity, when the projectile reaches the point E, which is in the same horizontal plane to the point of projection O, will be same as the horizontal component of initial velocity at the point of projection. Vx is always equal to ux. So but vy will be directed opposite to ui when it returns to the horizontal plane of projection. So mathematically you can write vy equal to minus ui or minus u sin theta. So tan alpha equal to vy by vx. So when the projectile returns to the horizontal plane of projection, or when it cuts the x-axis, we can write y equal to 0, and tan alpha equal to vy equal to minus u sin theta. Vx is same as ux equal to u cos theta. So you can write tan alpha equal to minus tan theta. Or mathematically you can write alpha equal to minus theta. That means when the projectile returns to the horizontal plane through the point of projection, it makes same angle theta with the horizontal. That means if the body is projected with initial speed u, an angle theta above the horizontal from a point O, when it returns to the horizontal plane through the point of projection, its velocity makes same angle theta but directed below the horizontal. Next, I would like to discuss about relative motion between two projectiles. This is usually not specifically discussed in the board examination syllabus, but you find some questions based on this discussion in competitive examinations. Let us consider two projectiles which are projected simultaneously from same vertical plane with different initial speeds u1 and u2. So one body is projected with initial velocity of magnitude u1 direct an angle theta 1 above the horizontal. Let us suppose second body is projected with initial velocity of magnitude u2 direct at an angle theta 2 above the horizontal. And let us suppose both the projectiles move in the same vertical plane. The vertical plane in which the projectiles move, I choose it as xy plane. Let us suppose the two projectiles move in the same vertical plane without colliding with each other during motion under influence of gravity. Then in general case, velocity of the projectile at time t after projection, we write I cap into Vx plus j cap into Vy. The horizontal component of velocity of projectile at any instant during the motion under influence of gravity, same as the horizontal component of initial velocity, which you can write as u cos theta. And vertical component of velocity at time t after projection can be found by using the equation v equal to u plus at for motion in the vertical direction. The vertical component of initial velocity can be written as equal to u sin theta. The acceleration in the vertical direction is equal to gt. So in vector form, the velocity at time t after projection is given by v bar equal to I cap into u cos theta plus j cap into u sin theta minus gt. So velocity of one of the projectiles at time t after projection is given by v1 bar equal to I cap into u1 cos theta 1 plus j cap into u1 sin theta 1 minus gt. The velocity of other projectile at the same instant of time is given by v2 bar equal to, for second projectile you can write au equal to u2 and theta equal to theta 2 on the right hand side. v2 bar equal to I cap into u2 cos theta 2 plus j cap into u2 sin theta 2 minus gt. So relative velocity of second projectile with respect to the first projectile, I denote it by v bar subscript 2 comma 1. That you can write v2 bar minus v1 bar. That means you have to subtract this equation from this equation. So gt gets cancelled on the right hand side. So you get u2 cos theta 2 minus u1 cos theta 1 into I cap plus u2 sin theta 2 minus u1 sin theta 1 into j cap. That means relative velocity of second projectile with respect to the first projectile is given by v bar subscript 2 comma 1 equal to u2 cos theta 2 minus u1 cos theta 1 into I cap plus u2 sin theta 2 minus u1 sin theta 1 j cap. You can observe that you don't find time t in the expression for v bar subscript 2 comma 1. V bar subscript 2 comma 1 represents the relative velocity of the second projectile with respect to the first projectile. You can observe that relative velocity of second projectile with respect to the first projectile when both are moving under influence of gravity at the same place, the same vertical plane, is independent of time t. That means relative velocity of one projectile with respect to other projectile does not change with time during the motion under influence of gravity. Therefore, we can say that the path followed by one projectile as seen from the another projectile is a straight line path. So you can observe two more special cases in this discussion. Suppose if the two projectiles have equal velocities in the horizontal direction, that means if u1 cos theta 1 is same as u2 cos theta 2. If u1 cos theta 1 is equal to u2 cos theta 2, the next component of the relative velocity between the two projectiles becomes 0. Then relative velocity of second projectile with respect to the first projectile will be acting in the vertical direction. Relative velocity of second projectile with respect to the first projectile will be acting in the vertical direction. Then there is no relative motion in the horizontal direction. Then v bar 2 1 will be equal to u2 sin theta 2 minus u1 sin theta 1 j cap. That means relative velocity of second projectile with respect to first projectile will act in the vertical direction if the horizontal components of the two projectiles are equal. Suppose if the vertical components of the two projectiles are equal, if u1 sin theta 1 equal to u2 sin theta 2, in that case the y component or vertical component of relative velocity between the two projectiles becomes 0. Then the relative velocity of second projectile with respect to the first projectile will act only in the horizontal direction. So you can write u2 cos theta 2 minus u1 cos theta 1 into I cap. That means you can substitute this term 0. That means if vertical components of initial velocity of the two projectiles are equal, then the relative velocity of the two between the two projectiles acts in the vertical horizontal direction. So the path followed by one projectile related to other projectile will be in the horizontal line if vertical components of initial velocity are equal. So this part of the discussion I have not shown you in the PowerPoint presentation earlier. I have not given the notes for this part of the discussion. Therefore, if you want to copy the working, you can copy this. You can take a pause and copy this working. That means the conclusion you have to remember is that if we consider two projectiles which are thrown simultaneously into the same vertical plane at a given place so that both move under influence of gravity, then the path followed by one projectile with respect to other projectile will be a straight line path, because the relative velocity between the two projectiles does not change with time. And if the horizontal components of the two, if the horizontal components of velocity of the two projectiles are equal, then the relative velocity of one projectile with respect to other projectile will act in the vertical direction. In case if the vertical components of initial velocity of the two projectiles are equal, but horizontal components of velocity are different, in that case, the path followed by one projectile relative to other projectile will be a horizontal line. Then the relative velocity between the two projectiles will be directed in the horizontal direction. So in the next class, I will be discussing the problems from the assignment in oblique projection. So I have, after the going through this theory part of the oblique projection of the projectile motion, so I have included one assignment in the projectiles. The first 40 questions in the assignment are based on the oblique projection. You first try to go through those 40 questions in the assignment on oblique projection. You can try to first answer them, try to work out them yourself, try to work out as many questions as you can solve, and check up your answers in the last. Then next class I am going to do the discussion of these problems. In case you are able to solve almost all the questions in the assignment yourself, you can skip my class for discussion of the questions. You can directly go to the next class. So I am going to show you the questions. You can see the questions that are fed into the computer in continuation of this class. Then after going through the question, you can also go through the solutions for the questions in case you have doubts in some of the questions in the assignment. So there is one more conclusion which I would like to discuss, which can be used directly while solving multiple choice questions. In some of the problems, you may be asked to find the time after projection at which the velocity of the projectile will be perpendicular to the initial velocity of projection. In vector form, the velocity of projectile at time t after projection can be written as v bar equal I cap into Vx plus j cap into Vy. And the initial velocity of projectile in vector form, we can write u bar equal I cap into Ux plus j cap into Uy. I would like to find the time after projection at which the velocity of the projectile is perpendicular to the initial velocity of projection. That means you have to find, we are going to find the time after projection at which v bar is perpendicular to u bar. So when v bar is perpendicular to u bar, when v bar dot u bar becomes 0. So v bar dot u bar can be written as Vx Ux plus Vy Uy. As I have discussed earlier in vectors, if two vectors A bar and B bar are perpendicular, the dot product of the two vectors will be 0. Vx you can write u cos theta. Ux is also equal to u cos theta. The horizontal component of initial velocity of projectile is equal to u cos theta. The horizontal component of final velocity will be same as the horizontal component of initial velocity, which will be equal to u cos theta. Vertical component of initial velocity is given by Uy equal to u sin theta. Vertical component of final velocity of time t is given by Uy plus Ay into t. That is using the equation v equal to u plus at for motion in the vertical direction. Uy can write u sin theta. Acceleration Ay in the vertical direction can be written as minus g. So you can substitute here Vx equal to u cos theta, ux equal to u cos theta, Vy equal to u sin theta minus gt, and Uy equal to u sin theta. So you get, simplify this, get u square cos square theta plus u square sin square theta minus gtu sin theta. You can take u square common in the first two terms on the left hand side, and the third term we can carry it to the right hand side. Cos square theta plus sin square theta will be equal to 1 for any value of theta. Can carry the factor gu sin theta to the other side of the equation. So the time after projection at which V bar is perpendicular to U bar is given by T equal to U by G sin theta. Of course, this conclusion is valid only when this time T is not less than, is not more than the time of flight of the projectile. This conclusion is valid. So in general, if the body is projected at an angle theta above the horizontal, you can conclude that V bar is perpendicular to U bar at the instant of time T equal to U by G sin theta. This conclusion is valid when the above instant is during the time of flight. That means this should be less than the time of flight. The time of flight is given by 2u sin theta by g. So 1 by 2 is less than sin square theta. Or sin square theta should be greater than 1 by 2. Because the angle of projection is greater than, the angle of projection is less than 90 degrees. So sin theta should be taken positive. Sin theta greater than 1 by root 2 or theta greater than 45 degrees. Because sin 45 degrees is 1 by root. That means if the angle of projection of the projectile is greater than 45 degrees, then the velocity v bar will be perpendicular to u bar at the instant of time t equal to u by g sin theta. If you want to copy this working, you can copy the working, you can take a pause and copy the working. I will be showing the problems and assignment in projectiles in next class.